In this lecture, we will be covering the concept of conditional variance. So first, let's remind ourselves of the definition of variance of a random variable. So x will be a square integrable, which means the expectation of x squared is finite, real valued random variable on probability space omega fp. Recall omega is our set of outcomes. F is our sigma algebra of events. So that's a special set of subsets of omega, and p our probability measure. The variance of x is defined as the expectation of the square of the deviation of x from its mean. In financial modeling, it is common and standard to assume constant volatility or standard deviation for many types of stochastic processes. In particular, if you have returns or losses. So suppose we were looking at returns or log returns as a process, then the variance of those returns, if we take the square root to get a standard deviation, this is what we would call the volatility. And in reality, it is often the case that time series or stochastic processes like returns do not exhibit constant volatility. And so it's important to start to expand our class of models for time series and stochastic processes to incorporate some type of change in volatility. And one of the things that we introduced to do that is we introduced the concept of conditional variance, which gives us the concept of a conditional volatility. So our definition of conditional variance is very similar to the definition of variance, with the one modification that all expectations are changed to conditional expectation. So we're in the same scenario where we have x, a square integrable, real valued random variable on our probability space, but now we have g, script g, being a sub-sigma algebra of script f. And recall that in measure theoretic probability, we can think of these sigma algebras as collections of events. And they're events that we can feed to the probability measure and get probabilities of the events in these collections. And because G and F represent collections of events, we can interpret them as sets representing information. So our script G here is contained in our script F, and this means G has less information than what you have if you have F. So the idea behind this definition of conditional variance of x given G is it's the variance of x given G, meaning your expectations are replaced with conditional expectations, conditioning on what you know from information set G. And so you can think of this as, what is your guess at the variance of x if this G represents your information set? We can take that idea and extend it to the conditional variance of x given the random variable y by replacing the G's with y's, and recall that this type of expectation, it's really shorthand for the expectation of x given sigma of y, where sigma of y represents the smallest sigma algebra generated by the random variable y. But again, the key thing to remember here is information. So what is your guess at the variance of x given this information in G, or given the information encoded in the random variable y? Now, when we look at modeling, we know a standard approach is really regression. And so in that case, we have p predictor variables, so x1, x2 up through xp, each one at time t. And we have a response variable yt. And so the idea is that you have a time series of data where you have p predictors and one response, and you have one p plus one tuple for every time instance. And then we model the uncertainty with a white noise term. So epsilon t is white noise, mean zero, variance sigma epsilon squared, and the idea is that the epsilon t's are all uncorrelated with one another. So our standard form of a regression is written in this way. So our response is equal to some deterministic function of the predictors plus a noise term. And we can check that in this framework, we do in fact have a constant conditional mean and a constant conditional variance. So we check first for the mean, and the conditional mean of the response given the predictors will just be this prescribed function of the predictors. So to compute this conditional expectation, we first replace yt with what we have from its definition in equation 4, f of x1t up to xpt plus epsilon t given x1t up to xpt. And first we know conditional expectation is linear, so the expectation of the sum is the sum of the expectations. So this becomes the expectation of f of x1t up to xpt given x1t up to xpt plus the expectation of epsilon t given x1t up to xpt. And now we use properties of conditional expectation. First, this f is a function of the variables that we know. So this term here is known by our information set on which we are conditioning. And so we use that property that it can be then taken out of the expectation. And so this first term would be f of x1t to xpt times the expectation of 1 given this other information, which is just 1. So this becomes f of x1t up to xpt. And for the second term, we note that the epsilon t is independent of these predictors, which is a standard assumption that we make in a regression model. The white noise, besides being uncorrelated amongst themselves, are also independent of these predictor variables, which means we lose the conditioning. And so this term becomes the expectation of epsilon t, which we know is 0 because it's a mean zero white noise process. So we see that this conditional mean of y given the predictors, is nothing more than f of x1 to xp. For our conditional variance, we have a bit more of bit more work to do with the calculation. So the first thing we do to do this conditional variance is write down the actual definition of conditional variance. So we know that we have, and we can use some colors, our outer expectation. So it's the conditional expectation of yt minus, and this will be our inner conditional expectation, the expectation of yt given x1t up to xpt, that quantity squared, but that outer expectation is a conditional expectation. So conditioning on x1t up to xpt. So again, this is the definition of your conditional variance. And note that we are just we're using the definition of variance, but replacing the expectations with conditional expectations. Now we can use the definition of yt and the fact that we calculated this in the previous step. So note the definition of yt is from equation 4, our regression model. So we can incorporate that. So yt is that f of x1t up to xpt plus epsilon t. But then note that this conditional expectation we just calculated as f of x1t up to xpt. And so we can make that substitution. And so that is from our previous step. So minus f of x1t up to xpt all of that squared, and we retain that outer conditional expectation. And we now notice that these f's cancel. And what remains will be the expectation, conditional expectation, given x1t up to xpt of all that remains in the integrand here is epsilon t. So the expectation of epsilon t squared given x1t to xpt. But again, we use our argument that epsilon t is independent of the predictors, which means we can drop the conditioning. The extra information does not affect our expectation of epsilon t squared, and so we're left with the expectation of epsilon t squared, which because, recall, epsilon t is a white noise with mean 0. So since it has a mean 0, this is in fact the variance of epsilon t, which in our model is sigma sub epsilon square. So we see that in this model, so this is just we're just rewriting what our model is, our regression model. We see that the conditional expectation of the response, given the predictors, is just this prescribed function of the predictors. And the conditional variance of yt, given the predictors, is our sigma sub epsilon square. This is a very standard and common model to use in financial modeling. Perhaps the most common and the most famous example of this is that of multiple linear regression. And so in the case of multiple linear regression, our function f is this linear function of the predictor variables. And we see we have beta coefficients. And typically you are fitting this using an ordinary least squares routine. So this is a very common and standard approach in financial modeling, or really in any kind of time series modeling. But again, the issue is we don't really believe that we have a scenario where we have constant variance. And it can be hard to move to a class of models where we have non-constant variance, but we have this very nice ability to come up with models where we have non-constant conditional variance. So again, in this case, knowing these predictors, it doesn't help us guess at the variance of y, because the variance of y is sigma sub epsilon square, which matches the conditional variance of y. And so the idea here is in these standard models, being given this predictor information doesn't help us improve on our guess of what the variance of y is. It doesn't give us more information to refine it. It's nothing more than the unconditional variance of y. Now, we should also mention that we are modeling a constant mean in the sense that our conditional mean of yt is just coming from the predictor function itself. We can get constants, we can get models where you have a non-constant conditional mean. One model that we use for that we've seen in a previous lecture called ARMA models, or autoregressive moving average models. And we can use these types of models for that. In particular, if you look here, we have a white noise process, and then our ARMA PQ remembers parts of itself from the past, and it remembers parts of its previous noise terms. And it's using that to give you a model for how yt differs from its mean. So it differs from its mean today with some type of memory for how it differed from the mean yesterday, all the way down to p days before, and also some memory on the previous noise terms going back q days. This can give you a model where you can actually condition on these previous values, these previous terms, to have a guess at the conditional expectation of yt. We leave that for a future lecture, but it is important to note that we do have models for non-constant conditional means. And for non-constant conditional variance, we are introducing the term of heteroscedasticity. So we say a time series or a stochastic process exhibits heteroscedasticity if it has a non-constant variance. We also have this other version where a time series exhibits conditional heteroscedasticity if it has a non-constant conditional variance. And the way that's the type of property that we are going to incorporate into our model. And the way we do that is to really note that what we're concerned about is going to be our white noise term. So in our standard regression models, we can think of this as this prescribed function of the predictors as our conditional mean, plus a white noise term. And we are going to modify this to allow non-constant variance, or rather non-constant conditional variance. And the way we modify this is via the noise term. So we actually can introduce an entire class of models, all of which are focused on building a new noise term. And the basic mechanism we're going to use for that is to scale it. So first, note that we change our noise terms a bit, and we actually make them white noise 0, 1, or you may call it a standard white noise. Once we do that, well, and we also rename them, we call them innovations. With that, we introduce a function, sigma, of these predictors, and that scales our innovations. And so you can now think of this as a new type of white noise term, which we will call here a scaled white noise. And this new noise term, so this sigma of your predictors times epsilon t, the idea is it's going to build in some memory. And the key aspect of it is it builds in memory for the conditional variance of yt. So the variance of yt given the predictors will be this function sigma squared. And note, it becomes instrumental that the white noise terms have a variance of 1, so that this conditional variance is going to be completely dependent on this sigma, because the variance of the epsilon t is 1. And we'll see how this works in some future lectures, but it's important to also note that, number one, we require that our sigma function be non-negative, because it represents a standard deviation. So a standard deviation must be non-negative. And if it's linear, its coefficients must be constrained. So the solution is we will use nonlinear functions for this sigma. And that will take us to what are called Arch and Garch models. And we see that the H stands for heteroscedasticity, the C for conditional. So this will be autoregressive, conditional heteroscedasticity. And then the G is generalized, autoregressive, conditional heteroscedasticity models. And the idea here is conditional heteroscedasticity, what we just described. We want to have a non-constant conditional variance. Autoregressive will mean that conditional variance of yt given the predictors, will be able to remember something about previous values. So that's the natural next step, is to go to the Arch and the Garch model. But the key thing to recognize when you want to introduce conditional heteroscedasticity to a time series model, you move from your standard white noise type of process. Well, you move from a white noise to a standard white noise, mean 0 variance 1, and then you scale it by just the right function. And that will introduce conditional heteroscedasticity. But the models we will focus on will not introduce heteroscedasticity. So we will see models that have a constant variance, a constant unconditional variance, but a non-constant conditional variance.